Somewhere in deep space, approximately 3 billion light-years from here, something is pulsing. It is not an ordinary star, not a random explosion. It is a signal that repeats. Every fraction of a second, a pulse of radio waves crosses the cosmic void with a regularity that defies simple explanations. Earth's radio telescopes have been capturing these flashes since 2007, and since then astrophysicists have cataloged hundreds of them, trying to decipher what could produce them with such precision and such energy. You are lying down now, perhaps already with your eyes closed, and as you breathe gently, these signals continue arriving. They cross entire galaxies, deflect around clouds of gas and dust, and eventually reach the antennas we have built in remote deserts and silent mountains. Each pulse carries information about unimaginable distances and physical processes we do not yet fully understand. There is something in this repetition that invites contemplation, a cosmic cadence we will return to explore later, when sleep is already closer. The universe is surprisingly silent to our ears, but extraordinarily noisy to our instruments. If we could translate all the electromagnetic waves crossing space into audible sounds, we would be immersed in a constant symphony of noises, crackles, and hums. Stars emit across various frequencies. Black holes generate jets that radiate energy. Pulsars spin and sweep the cosmos with beams of radiation like distant lighthouses. It is in this scenario of invisible activity that repetitive signals stand out, not by their volume, but by the strangeness of their regularity. Scientists call these phenomena fast radio bursts, or FRBs. The name is technical, but the reality behind it is almost poetic. They are pulses of energy lasting milliseconds, sometimes less than the blink of an eye, yet releasing in fractions of a second the same amount of energy the sun produces in days. Most of these signals appear once and never repeat, making them nearly impossible to study in detail. But some return, they repeat, and this repetition is what transforms curiosity into scientific fascination. When a signal repeats, astronomers can point their telescopes at the same region of the sky and wait. They can collect more data, refine their measurements, try to understand the pattern. And this is how they discovered that some of these sources pulse with regular intervals, as if there were a cosmic clock marking time on scales that defy our intuition. What could create such precision in such extreme environments? This question remains partially open. Known physics offers some possibilities. Neutron stars with absurdly intense magnetic fields, called magnetars, are the most likely candidates. These objects, only 20 kilometers in diameter, but with masses greater than the Sun, spin rapidly and possess magnetic fields trillions of times stronger than Earth's. Under certain conditions, they can release energy in pulses that cross the universe. But even this explanation raises new questions about the exact mechanisms involved. Tonight, as you settle into sleep, we will journey together through this landscape of distant signals. There is no rush to reach conclusions, no urgency to solve all the enigmas. What exists is the invitation to contemplate, to let the mind float between collapsed stars and radio waves that travel for billions of years before reaching us. Each pulse that arrives at Earth is a messenger of events that happened when our planet did not yet exist. And there is something deeply reassuring in knowing that the cosmos continues its silent work while we, down here, simply rest. Before we go deeper into this journey through signals that cross the universe, I want to tell you I am truly glad you are here with me tonight. If you are finding this exploration comforting, if you enjoy this different way of thinking about reality as you relax, please consider subscribing to the channel, leaving a like, or sharing this with someone who might need help sleeping. A comment telling me you are here, listening, also means a great deal. These nighttime journeys through the mysteries of the cosmos are created especially for moments like this, when you want your mind engaged in something deep and beautiful while your body relaxes into sleep. And if you ever find yourself struggling with insomnia, or just need something gentle to help you drift off, come back to this. Let it become a familiar companion in those quiet hours when sleep feels far away. That is what it is here for, to guide you softly into rest night after night whenever you need it. The story of fast radio bursts begins with an accident, as many discoveries in astronomy do. In 2007, an astrophysicist named Duncan Lorimer was reviewing archival data from the Parkes radio telescope in Australia, searching for something else entirely. He was looking for pulsars, those spinning neutron stars that emit regular beams of radio waves, when he noticed something unusual in the data. A single intense burst of radio energy had been recorded in 2001, lasting only 5 milliseconds, but releasing an extraordinary amount of energy. The signal came from a direction in the sky that pointed far beyond our galaxy, suggesting a source billions of light-years away. At first, the scientific community was skeptical. A single detection could be anything: an instrument glitch, interference from human technology, a statistical anomaly. But Lorimer and his colleague David Narkovich analyzed the data carefully and found that the signal had characteristics consistent with having traveled through intergalactic space. The radio waves showed signs of dispersion, a spreading out of frequencies that happens when radiation passes through clouds of electrons between galaxies. The amount of dispersion indicated a truly cosmic origin. This first detection, now known as the Lorimer burst, opened a door to an entirely new field of astrophysics. If such powerful signals existed, there had to be more of them. And indeed, as astronomers began searching specifically for fast radio bursts, they started finding them. Not frequently, because each one lasts such a short time and comes from an unpredictable direction, but regularly enough to confirm that these were real phenomena occurring throughout the universe. Imagine lying beneath a vast dark sky, not with your eyes, but with an enormous radio antenna, listening to the cosmos. Most of what you hear is background noise, the gentle hiss of the cosmic microwave background, the steady signals from known pulsars, the occasional crackle of solar activity, and then, without warning, a flash. A burst of energy so brief you might miss it if you blinked, but so powerful it outshines everything else in that moment. Then silence again. The sky returns to its usual murmur. You wait, but the flash does not repeat. It was there, undeniably real, and now it is gone. This is what makes fast radio bursts so challenging to study. Most of them are one-time events. They happen once, somewhere in the distant universe, and never occur again from the same source. By the time astronomers realize a burst has happened and try to point other telescopes at its location, there is nothing left to see. The event is over. All that remains is the data recorded in that fraction of a second, and the questions about what could have caused it. The energy involved is staggering when you consider the distances. A typical fast radio burst releases as much energy in a few milliseconds as the sun produces in an entire day. Some of the more powerful bursts release in that instant what the sun produces in months. And this energy is being generated billions of light-years away, meaning it has traveled across a significant fraction of the observable universe to reach our detectors. Whatever is creating these bursts must be an extraordinarily efficient engine, converting some form of stored energy into radio waves with remarkable intensity. Several theories emerged in those early years. Perhaps fast radio bursts were the death cries of stars, the final moments of some cataclysmic collapse. Perhaps they were the result of two neutron stars colliding, an event so violent it warped space-time itself. Perhaps they were signals from advanced civilizations, though most scientists considered this unlikely given the apparent randomness and the extreme energies involved. The truth was, nobody knew. The bursts were too rare, too brief, and too unpredictable to allow for detailed study. What astronomers needed was a repeater, a source that would burst not once but multiple times, allowing them to observe it repeatedly, to study its behavior, to pinpoint its exact location in the sky. For years, this seemed like a distant hope. Every new burst detected appeared to be a unique event, flashing once and then falling silent forever. The universe seemed full of these brief whispers, but none of them wanted to speak twice. And then, in 2016, everything changed. A repeating source was finally found. It was designated FRB 121102, named for the date of its first detected burst in 2012. But unlike all the others, this one came back. Again and again, astronomers pointed their telescopes at its location and caught burst after burst, sometimes dozens in a single hour. The whisper had become a conversation, and for the first time, scientists could truly begin to listen. As you breathe slowly and let your body sink deeper into rest, consider this image. Somewhere in a dwarf galaxy 3 billion light-years away, something is pulsing. It has been pulsing for longer than Earth has existed. The light from that galaxy, the radio waves from those bursts, have been traveling toward us since before the first complex life appeared on our planet. And now, in this moment, those ancient signals are being captured by antennas built by creatures who evolved on a small rocky world orbiting an ordinary star. The cosmos speaks, and we have only just learned to listen. When astronomers finally had a repeating source to study, they could begin asking deeper questions. What kind of object could produce such powerful bursts of radio energy, not once but hundreds of times? The answer, they suspected, lay in one of the most extreme objects the universe can create, a magnetar. To understand what a magnetar is, you first need to understand what happens when a massive star dies. Stars spend most of their lives in a delicate balance, the outward pressure of nuclear fusion in their cores pushing against the inward pull of gravity. As long as fusion continues, the star remains stable, but eventually, the fuel runs out. For stars much larger than our Sun, this marks the beginning of a dramatic end. When fusion stops, there is nothing left to counteract gravity. The core of the star collapses inward with incredible speed, compressing matter to densities beyond anything we experience on Earth. Protons and electrons are squeezed together to form neutrons, and what remains is a neutron star, an object containing more mass than the Sun packed into a sphere roughly 20 kilometers across. A teaspoon of neutron star material would weigh billions of tons. This collapse also does something remarkable to the star's magnetic field. Just as a spinning figure skater pulls in their arms and spins faster, the collapsing core compresses the magnetic field lines, amplifying them enormously. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. But some neutron stars, through processes still not entirely understood, develop magnetic fields 1,000 times stronger still. These are magnetars, and their magnetic fields are the most powerful known in the universe. Imagine a magnetic field so intense that it would erase the magnetic strip on a credit card from halfway across the solar system. A field so powerful that it distorts the very structure of atoms, stretching them into long, thin cylinders aligned with the field lines. A field so extreme that it affects the vacuum of space itself, causing light to behave in strange ways as it passes through. This is the environment of a magnetar, and it is within this environment that fast radio bursts may be born. The leading theory suggests that magnetars produce fast radio bursts through sudden releases of magnetic energy. The intense magnetic field of a magnetar is not static. It is constantly shifting and rearranging itself, building up stresses in the crust of the neutron star. When these stresses exceed a certain threshold, the crust cracks, releasing enormous amounts of energy in a violent event called a starquake. This energy can propagate outward as a burst of radio waves, brief but incredibly powerful. In April 2020, astronomers received confirmation that magnetars could indeed produce fast radio bursts. A magnetar within our own galaxy, known as SGR 1935+2154, emitted a burst that was detected by multiple radio telescopes. This was the first time a fast radio burst had been definitively linked to a specific type of astronomical object. The magnetar had spoken, and we had caught it in the act. But even this discovery raised new questions. The burst from the galactic magnetar was powerful by local standards, but it was thousands of times weaker than the extragalactic fast radio bursts coming from billions of light-years away. If magnetars are responsible for all fast radio bursts, then the distant ones must be produced by magnetars far more active or far more powerful than any we have observed in our own galaxy. What makes some magnetars so much more energetic than others? We do not yet know. There is also the question of the repeating pattern. Some fast radio bursts repeat with apparent regularity, showing periods of activity followed by periods of silence. One source, FRB 1809-16, was found to have a cycle of approximately 16 days, bursting for about 4 days and then falling silent for 12. Another, FRB 121102, shows a possible cycle of about 157 days. What could cause such long-period variations in a magnetar's activity? One possibility is that the magnetar is in a binary system, orbiting another star, As it moves through its orbit, it might pass through regions of denser material that trigger bursts, or its orientation relative to Earth might change in ways that affect whether we can detect its emissions. Another possibility is that the magnetar itself has a slow wobble or precession, like a spinning top that gradually tilts, changing the direction of its radio beams over time. As you lie here letting these ideas drift through your mind, picture a sphere of matter denser than an atomic nucleus, spinning several times per second, wrapped in magnetic field lines of unimaginable intensity. Every now and then, the crust shifts, and a pulse of energy shoots out into space at the speed of light. That pulse travels for millions or billions of years, crossing the vast emptiness between galaxies until it finally washes over a small blue planet where curious creatures have built machines to catch it. The magnetar does not know we are listening. It simply does what physics demands, releasing energy according to laws written into the fabric of the universe. And we, in our brief moment of existence, have learned to hear its heartbeat. There is something peaceful in this image. The magnetar will continue pulsing long after we are gone, long after our civilization has risen and fallen, perhaps long after Earth itself has been swallowed by an expanding sun. These signals connect us to timescales far beyond human comprehension, reminding us that we are part of something vast and ongoing. Tonight, as sleep approaches, let that vastness hold you gently. You are made of the same matter that forms those distant stars, governed by the same laws that make them shine and pulse. In a very real sense, you are the universe experiencing itself, and the signals from deep space are messages from your cosmic family, reminding you that you are never truly alone. Detecting signals from billions of light years away requires some of the most sensitive instruments humanity has ever built. Radio telescopes, unlike optical telescopes that gather visible light, are designed to capture radio waves, a form of electromagnetic radiation with much longer wavelengths. These waves can pass through clouds of gas and dust that would block visible light, allowing astronomers to see parts of the universe that would otherwise remain hidden. The dishes you might picture when thinking of radio telescopes, those enormous curved surfaces pointing at the sky, work by collecting radio waves and focusing them onto a receiver. The larger the dish, the more waves it can collect, and the fainter the signals it can detect. Some of the most famous radio telescopes in the world have dishes spanning hundreds of meters. The Arecibo telescope in Puerto Rico, before its collapse in 2020, had a dish 305 meters across, nestled into a natural depression in the landscape. The 500-meter aperture spherical telescope in China, known as FAST, is even larger, currently the biggest single-dish radio telescope on Earth. But detecting fast radio bursts presents a particular challenge. Because they are so brief, lasting only milliseconds, and because they can come from any direction in the sky at any time, astronomers cannot simply point a telescope at one spot and wait. They need instruments that can monitor large portions of the sky simultaneously, capturing any burst that happens to occur within their field of view. This is where a new generation of radio telescopes comes in. Instruments like the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, are designed not as single dishes, but as arrays of cylindrical reflectors that together monitor a wide swath of sky. CHIME, located in British Columbia, can observe about 200 square degrees of sky at once, roughly 1,000 times the area covered by the full moon. Since it began operations in 2018, CHIME has detected hundreds of fast radio bursts, vastly increasing the number of known sources. When a burst is detected, the data is analyzed to extract as much information as possible. The dispersion of the signal, the way different frequencies arrive at slightly different times, reveals how much material the radio waves passed through on their journey. This allows astronomers to estimate the distance to the source, the polarization of the signal, the orientation of the electromagnetic waves can reveal information about the magnetic environment near the source. The brightness and duration of the burst constrain the size and energy of the emitting region. With enough data from enough bursts, patterns begin to emerge. Some sources are clearly prolific repeaters, bursting dozens or hundreds of times. Others seem to burst only once or perhaps repeat on timescales longer than we have been observing. The distribution of bursts across the sky appears random, consistent with sources scattered throughout the distant universe, and the rate of bursts when accounting for observational biases suggests that thousands of fast radio bursts occur somewhere in the observable universe every day. Consider that for a moment as you breathe slowly. Every day, thousands of these signals flash somewhere in the cosmos. Most of them are never detected by anyone, their pulses washing over Earth and continuing outward into space without leaving any record of their passage. Our telescopes catch only a tiny fraction, those that happen to occur in the direction we are looking at the moment they arrive. The universe is full of these whispers, a constant rain of signals from sources we are only beginning to understand. There is also the question of what the signals can tell us about the universe itself. Because fast radio bursts travel such enormous distances, they pass through the intergalactic medium, the sparse clouds of gas and plasma that fill the space between galaxies. This material leaves its mark on the signals, dispersing them in ways that depend on how much material they encountered. By studying this dispersion, astronomers can map the distribution of matter in the universe, including the elusive baryonic matter that makes up atoms, but that is difficult to detect directly because it emits so little light. In a sense, fast radio bursts are like cosmic flashlights, illuminating the otherwise invisible material between galaxies. Each burst that reaches us carries information not just about its source, but about everything it passed through on its journey. The universe has become a laboratory, and these brief pulses of radio energy are one of our tools for exploring it. As you rest here, imagine yourself as part of this vast network of listening. Right now, somewhere in the mountains of British Columbia, cylindrical reflectors are gathering radio waves from the sky. In the Australian outback, dishes are turning slowly to track a particular patch of stars. In China, the enormous FAST telescope sits in its karst depression, its surface rippling gently in the wind as it listens to the cosmos. And all around the world, data is flowing into computers, being searched by algorithms designed to spot the brief signatures of fast radio bursts among the noise. This is humanity at its most curious and most patient. We build machines to hear whispers from billions of light years away, signals that began their journey before complex life existed on Earth. We do this not because it has obvious practical application, but because we want to understand. We want to know what is out there, what kinds of processes can produce such extraordinary events, what the universe is doing when we are not watching. And slowly, one detection at a time, we are beginning to find out. The night sky above you, if you could see it, would appear calm and unchanging. The stars in their familiar patterns, the planets on their steady paths, the moon in its eternal orbit. But beneath that apparent stillness, the cosmos is alive with activity. Signals are crossing the void at every moment, carrying information about events happening in galaxies so distant their light has not yet reached us. And you, lying here in the quiet darkness, are connected to all of it. The atoms in your body were forged in ancient stars. The calcium in your bones, the iron in your blood, the oxygen in your breath, all of it was created in stellar furnaces and scattered across space by stellar explosions. You are stardust that has learned to wonder about the stars. Tonight, let that wonder accompany you into sleep. When humans detect a signal from space that repeats with regularity, a certain question inevitably arises in the back of the mind. Could it be intentional? Could these signals be messages from an alien civilization, attempts at communication from beings we have never met and may never meet? It is a question that scientists are careful about, because the history of astronomy is filled with examples of natural phenomena that were initially mistaken for artificial signals. When pulsars were first discovered in 1967, their regular clock-like pulses seemed so artificial that the astronomers who found them half-jokingly named the first one LGM-1 for little green men. It took time and careful analysis to determine that pulsars were spinning neutron stars, natural objects producing natural signals through well-understood physics. The lesson was clear. The universe can create remarkable regularity through entirely natural means. A repeating signal is not by itself evidence of intelligence. Fast radio bursts have occasionally attracted similar speculation. Their extreme energies, their cosmic distances, their mysterious origins, all these factors can fuel imagination. But the scientific consensus is firmly that these signals have natural explanations. The association with magnetars, the consistency with known physics, the lack of any encoded information that would suggest intentionality, all point toward astrophysical rather than technological origins. Yet the question itself is worth contemplating, not because fast radio bursts are alien signals, but because it reveals something about how we relate to the universe. When we look at the stars, we cannot help but wonder if anyone is looking back. This impulse is deep in our psychology, a consequence of being social creatures who evolved to detect agency and intention in our environment. We see faces in clouds, hear voices in static, and wonder about minds behind the lights in the night sky. The search for extraterrestrial intelligence, known as SETI, is a legitimate scientific endeavor that has been ongoing for decades. Researchers use radio telescopes to scan the sky for signals that show signs of artificial origin, patterns that could not be produced by any known natural process. So far, no such signal has been confirmed. The universe, as far as we can tell, has been silent when it comes to deliberate communication, but this does not mean we are alone. It only means we have not yet found evidence of company. There is a particular kind of loneliness in contemplating a vast universe that may be empty of other minds. Billions of galaxies, each containing billions of stars, many of those stars orbited by planets, and yet possibly no one else thinking, wondering, asking questions. It is a sobering thought. But there is also a particular kind of significance in it. If we are alone, then we are the only part of the universe that knows it exists. We are the cosmos becoming aware of itself, the only candle of consciousness in an otherwise dark expanse. And if we are not alone, if there are other minds out there, separated from us by distances so vast that communication would take millions of years, there is a different kind of comfort. It means that the universe has a tendency to produce minds, that consciousness is not a fluke, but a feature, something that emerges naturally when the conditions are right. In that case, even if we never communicate with another civilization, we would know that we are part of a larger family of thinkers scattered across the galaxies. Fast radio bursts, whatever their origin, remind us that the universe is active and dynamic. Even in the apparently empty space between galaxies, signals are traveling, energy is being released, physics is unfolding according to its laws. We are embedded in a living cosmos, not in the biological sense, but in the sense of constant activity, constant change, constant happening. The stillness of the night sky is an illusion created by the limitations of our senses. In reality, the universe is buzzing. As you lie here on the edge of sleep, consider what it means to be a creature capable of asking these questions. You are not separate from the universe. You are part of it. Your neurons firing, your thoughts forming, your consciousness arising from matter and energy. These are all processes governed by the same physics that governs magnetars and radio waves and the expansion of space itself. When you wonder about the meaning of signals from space, it is the universe wondering about itself. Perhaps meaning is not something we find in the signals themselves, but something we create through the act of listening. The fast radio bursts have no inherent meaning. They are simply energy propagating through space according to physical laws. But when we detect them, study them, build theories about them, we infuse them with meaning. We make them part of our story, part of our ongoing effort to understand our place in the cosmos. The meaning is in the questioning, not in the answers. Tonight, let this be a gentle thought to carry into sleep. The universe is not hostile or friendly. It simply is. But you, a brief flicker of awareness in the cosmic night, have the extraordinary ability to perceive it, to wonder at it, to find beauty and meaning in its workings. That is a gift, perhaps the greatest gift that physics has ever given to itself. Rest now and let the universe continue its silent operations while you dream. Tomorrow, the signals will still be arriving, and the questions will still be waiting. There is no urgency. There is only this moment, this breath, this gentle surrender to sleep. Science progresses by replacing old mysteries with new ones. Every answer we find reveals questions we did not know to ask. This is the nature of exploration, whether across the oceans of Earth or the electromagnetic ocean of space. We push the boundaries of knowledge outward, and the boundary always turns out to be larger than we thought. Fast radio bursts are still young as a field of study, barely 2 decades old since the first detection. In that time, we have gone from a single puzzling event to hundreds of known sources, from complete bafflement to plausible theories involving magnetars and extreme physics. But we have not solved the mystery entirely. There are still bursts that do not fit neatly into our models, still variations in behaviors that challenge explanation. Some sources repeat frequently, while others have never been seen to repeat despite extensive monitoring. Are these truly different types of objects, or are the non-repeaters simply repeaters that burst on timescales longer than our patience? Some bursts show complex structure, with multiple peaks within a single millisecond, while others are simple and smooth. What determines this structure, and what can it tell us about the environment where the burst was generated? There are also the truly strange cases that push the boundaries of what we think we understand. Some bursts have been detected with circular polarization, a characteristic that suggests extreme magnetic fields or unusual emission mechanisms. Some have shown variations on timescales of microseconds, implying that the emitting region is fantastically small, perhaps only a few kilometers across. How can so much energy be released from such a tiny volume in such a brief instant? The next decade will bring new instruments and new capabilities. Arrays of radio telescopes working together will allow for more precise localization of bursts, pinpointing their sources with sufficient accuracy to identify the specific galaxies and even the specific environments within those galaxies where they originate. More sensitive detectors will catch fainter bursts, revealing whether there is a continuous spectrum of energies or whether bursts come in distinct types. And coordinated observations across multiple wavelengths from radio to visible light to X-rays may catch other forms of emission happening simultaneously with the radio bursts, providing clues about the underlying physical processes. There is also the tantalizing possibility of using fast radio bursts as tools for cosmology, the study of the universe as a whole, because the dispersion of each burst depends on how much matter it passed through. A large sample of bursts at known distances could map the distribution of baryonic matter throughout the cosmos. This would complement other cosmological probes, helping to resolve tensions in our understanding of how the universe expands and evolves. As you drift closer to sleep, consider that you are living in a moment of discovery. The questions being asked about fast radio bursts today may have answers within your lifetime. The theories being debated will be tested by observations not yet made. The universe is slowly revealing its workings to us, one detection at a time, and you are part of the generation witnessing this unfolding understanding. But the mystery itself is also valuable. Separate from whatever solutions we eventually find, there is something nourishing about living with unanswered questions, about knowing that the cosmos holds secrets we have not yet uncovered. It keeps curiosity alive. It reminds us that there is always more to learn, that the universe is richer and stranger than our current understanding can capture. Complete knowledge would be a kind of ending, and we are nowhere near that end. The repeating signals from space will continue arriving whether we solve their mystery or not. They will continue pulsing in the same patterns that physics dictates, carrying energy across the cosmos according to laws older than the stars themselves. Our understanding will grow, refine, perhaps transform into something we cannot yet imagine. But the signals themselves are indifferent to our understanding. They simply are. And perhaps that is the deepest lesson of this exploration. The universe does not exist to be understood by us. It exists, and we have the remarkable opportunity to try to understand it. That opportunity is precious, not because we will succeed in understanding everything, but because the attempt itself enriches our brief lives. The questions we ask about distant magnetars and radio waves are questions about who we are and where we belong in the cosmic story. In asking them, we participate in something larger than ourselves. Tonight, let the mystery be a comfort rather than a frustration. Let the unanswered questions be like stars, distant points of light that guide rather than destinations that must be reached. You do not need to understand everything to appreciate the beauty of the cosmos. You do not need to solve all the puzzles to feel connected to the vast unfolding of existence. It is enough to know that the signals are out there, that the universe is active and dynamic, and that you, in this moment, are part of it. And so we arrive at this moment, which is not really an ending but simply a point of rest in an ongoing journey. The signals from deep space will continue arriving through the night, through the days and years to come, carrying their messages across distances that make human scales seem almost imaginary. 3 billion light-years is not a number the mind can truly grasp. It is a gesture toward vastness, an acknowledgement that we are embedded in something so much larger than ourselves. The magnetars, if that is indeed what produces these bursts, will continue their slow processes of magnetic stress and release. Their crusts will crack in starquakes we will never witness directly, and pulses of energy will radiate outward at the speed of light, spreading through the universe like ripples on an infinite pond. Some of those ripples will reach Earth and be caught by our instruments. Most will travel forever through space without encountering anything at all. Pure energy propagating through the void until the heat death of the universe dims everything to silence. But tonight, you do not need to think about heat death or the ultimate fate of the cosmos. Tonight is for rest, for the gentle surrender of consciousness to sleep.